For over a century, we've told ourselves a comforting story about time. We've said it flows, we've said it moves in one direction, from past to future, like a river we can never swim against. We've built entire theories, entire intuitions, entire lives around this one assumption. But what if that story is wrong? What if some of the very physicists who taught us to trust Einstein, the same scientists whose equations put men on the moon and satellites in orbit, have gotten something fundamental about time itself completely backwards? Today, we're going to look at a growing, genuinely unsettling body of work in modern physics that suggests exactly that time may not flow at all, that the universe's deepest equations don't actually need time to exist, and that some of our most trusted assumptions about the past, present, and future might need to be thrown out entirely. Welcome back to the channel, where we take the universe's strangest, deepest questions and break them down in plain language, in the spirit of Brian Greene, where physics becomes a story instead of a lecture. If you're new here, we spend our time exploring exactly this kind of question. Not just what physics says, but where physics itself still doesn't agree with itself. Before we dive in, if you want more videos like this, hit subscribe. Stay until the end because we're going to get into an idea that some physicists take completely seriously, and it might change how you think about your own existence. And if you're enjoying this, please hit like and share it with someone who loves this kind of thing. Let's get into it. Ask almost anyone what time is, and you'll get some version of the same answer: time flows. The past is fixed and gone. The future is open and undetermined, and now is the thin moving edge between them, a spotlight sweeping forward, illuminating one moment after another. This picture feels so obvious that it barely seems worth questioning. It's baked into our language. We say time passes, we look forward to things, we leave things behind us. But here's the problem. Nowhere in the fundamental equations of physics does this flow actually appear. Not in Newton's laws, not in Einstein's relativity, not in quantum mechanics. Every one of these theories describes the universe using equations that work perfectly well, whether you run them forward or backward in time. The flow, the sense that we're moving through moments one at a time, physics doesn't require it. We just assume it because that's how we experience it. So if the equations don't demand a direction, why does time feel like it only moves one way? The standard answer lies in the second law of thermodynamics. Entropy, or disorder, always increases in a closed system. Break an egg and it scatters. You never see the pieces spontaneously reassemble. This one-way tendency toward disorder is what physicists call the arrow of time. But here's where things get uncomfortable. For this explanation to work, the universe has to have started in an extremely low entropy state, an extraordinarily ordered beginning right after the Big Bang, from which everything has been unwinding ever since. The problem is, physicists don't actually have a solid explanation for why the universe began in such an unlikely low entropy state in the first place. Cosmologist Roger Penrose has pointed out that, statistically, a universe like ours starting in that condition is almost unimaginably improbable. And yet, it's the one basic assumption the entire arrow of time depends on. In other words, the reason time seems to flow forward rests on an assumption we can't fully justify. That's not exactly a comfortable foundation for one of our most basic intuitions about reality. Here's where things get genuinely strange, and where some physicists argue the mainstream picture of time breaks down entirely. When physicists try to combine quantum mechanics with Einstein's general relativity, the two most successful theories in physics, they run into what's literally called the problem of time. The key equation here, the Wheeler-DeWitt equation, developed in the 1960s by physicists John Wheeler and Bryce DeWitt, describes the quantum state of the entire universe, and it has an astonishing feature: the variable for time simply doesn't appear in it. Mathematically, this equation describes a universe that is, in some sense, frozen, a single, unchanging quantum state with no built-in notion of before or after at all. Physicists have spent decades trying to explain this away, arguing that time must be hidden inside the equation somehow, emerging only when we look at correlations between different parts of the universe, rather than some external clock ticking away. But no one has fully solved this problem, and it remains one of the most significant open puzzles at the heart of theoretical physics. If our most fundamental attempt to unify physics produces an equation where time doesn't exist, that raises an uncomfortable question: what if time isn't as fundamental as we've always assumed? Few physicists have taken this idea further than Julian Barbour, whose 1999 book, The End of Time, argues something radical. Time, as we normally understand it, doesn't exist at all. Barbour's proposal is that reality isn't a sequence of moments strung together like beads on a string. Instead, there are only individual, complete configurations of the universe, snapshots essentially, which he calls nows. Each now contains everything, the arrangement of every particle, and even our own memories of what feels like a past. According to Barbour, our sense that time is passing comes entirely from the fact that some of these nows happen to contain memory-like structures, records that make it feel like there was a moment before. But there's no actual motion between them, no flow, no ticking clock underneath it all. Just an enormous, timeless landscape of possible configurations. This is an extreme position, and most physicists don't fully agree with it. But it's taken seriously enough that Barbour has continued publishing peer-reviewed research on it for decades, and it directly echoes the strange, timeless character of the Wheeler-DeWitt equation we just discussed. If Barbour and the mathematics of quantum gravity are onto something, then the sense that you're living through a single moving now might be something your brain constructs rather than something the universe actually provides. This connects directly to an idea we've covered before, the block universe, where past, present, and future all exist equally, like pages in a book. Barbour's view goes even further, suggesting that even within that block, the very idea of moving from one page to the next might be an illusion layered on top of a timeless structure. Einstein himself, late in life, seemed to lean this direction. In a letter to the family of his close friend Michel Besso, he wrote that the distinction between past, present, and future is merely a stubbornly persistent illusion. He may have meant that more literally than most people realize. Does this mean free will doesn't exist? Not necessarily. This remains a deeply debated philosophical question, separate from the physics itself. Even physicists who question the flow of time disagree on what it means for choice and agency. If time doesn't flow, why do we remember the past and not the future? This connects back to entropy. Our brains, like everything else, are built from physical processes that only work in the low to high entropy direction, which is why memory only ever points backward. Is this idea accepted by mainstream physics? Not fully. It remains a minority, though seriously discussed, position. Most physicists still work with the assumption that time flows in some meaningful sense, even while acknowledging the deep puzzles this creates in quantum gravity. Physicist Lee Smolin, in his 2013 book, Time Reborn, makes an argument that directly opposes Julian Barbour's view. Instead of time being an illusion, Smolin argues that time is the most real thing in the universe, more fundamental, even than the laws of physics themselves. Smolin's reasoning goes like this. Physicists have long treated the laws of nature as fixed, eternal, unchanging things that exist outside of time. Like a cosmic rule book, the universe simply follows. But Smolin asks, where did those laws come from? Why these laws and not some other set? His radical proposal is that the laws of physics themselves might evolve over time, the way biological species evolve, shaped by something like natural selection operating across cosmic history, possibly even across the birth and death of universes inside black holes. If that's true, then time isn't just a backdrop the laws play out in, it's the very thing that makes change, and therefore the laws themselves, possible in the first place. This is a controversial position, and it hasn't been adopted by mainstream physics, but it represents a serious, published counter-argument to the idea that time is somehow less than fully real. This disagreement connects to a much older debate in philosophy of physics: presentism versus eternalism. Eternalism, which aligns with the block universe view we discussed in part 1, holds that past, present, and future are all equally real. The now is just wherever you happen to be standing in a fixed, unchanging, four-dimensional structure. Presentism, on the other hand, which Smolin's view leans toward, argues that only the present moment is truly real. The past no longer exists, the future doesn't exist yet. Time genuinely passes, and this passage is a fundamental feature of reality, not an illusion created by memory or entropy. Physicists have argued for decades about which of these views is actually compatible with relativity. Einstein's theory suggests simultaneity is relative, that now differs for different observers, which seems to favor eternalism. But presentists argue there might still be a way to preserve a genuine universal now through certain interpretations of quantum mechanics that seem to require an objective present moment for measurement to make sense. Neither side has definitively won this argument, and it remains one of the most contested questions in the philosophy of physics today. Here's something that surprised physicists in a completely different way: the discovery that some physical processes aren't symmetric in time after all. In 1964, physicists studying particles called kaons discovered a phenomenon called CP violation, a subtle asymmetry in how certain particles decay compared to their antiparticle counterparts. Under a related principle called the CPT theorem, this implies that at an extremely fundamental level, some physical processes actually do distinguish between forward and backward time, even at the level of quantum interactions between individual particles. This was a big deal because for decades, physicists had assumed the fundamental laws were essentially time-symmetric, with only large-scale statistical effects, like entropy, creating an apparent arrow of time. CP violation showed that time's arrow might be baked in more deeply than anyone expected, not just an emergent statistical illusion, but something present in the basic rules governing matter itself. This discovery earned physicists James Cronin and Val Fitch the Nobel Prize in 1980, and it remains one of the key pieces of evidence cited by physicists who argue time is more fundamentally real than the timeless equations of quantum gravity suggest. A more recent, genuinely creative attempt to resolve this whole debate comes from physicists Alain Kahn and Carlo Rovelli, who proposed something called the thermal time hypothesis in the 1990s. Their idea, what we experience as the flow of time, might not be a fundamental feature of the universe at all, but something that emerges from the statistical, thermodynamic relationships between whatever limited part of the universe we happen to be observing. In other words, time might be less like a river running through reality and more like temperature, a useful, meaningful concept that only makes sense when you're looking at a system from a particular, limited point of view, rather than the whole thing at once. Carlo Rovelli expanded on this idea in his popular book, The Order of Time, arguing that if you could somehow see the entire universe from the outside with perfect, complete information, the very concept of time passing might simply dissolve. It's an artifact of our limited, coarse-grained perspective, not a fundamental property of reality itself. This idea attempts to bridge the gap between Barber's timeless universe and Smolin's insistence that time is real, suggesting that both might be capturing part of the truth depending on what scale and what perspective you're looking from. At this point, you might be wondering, how can some of the smartest people on the planet disagree this fundamentally about something as basic as time? The honest answer is that we don't yet have a complete theory of quantum gravity, the framework that would successfully combine quantum mechanics and general relativity into one consistent description of reality. Until that theory exists, physicists are left interpreting incomplete mathematical clues, each pointing in a slightly different direction, and each consistent with everything we've actually been able to measure so far. This isn't a sign that physics is broken. It's a sign that we're standing at the edge of what we currently understand, looking into genuinely uncharted territory. Some of the greatest breakthroughs in the history of science came from exactly this kind of foundational disagreement, resolved only decades later by new mathematics, new experiments, or entirely new ways of thinking about the problem. So where does this leave us? We've seen that some physicists, backed by the strange, timeless mathematics of the Wheeler-DeWitt equation, believe time itself might be an illusion, a story our brains tell us layered on top of a frozen, unchanging universe. We've also seen that other physicists, pointing to real experimental discoveries like CP violation, argue time is not only real, but possibly more fundamental than the laws of physics themselves. And in between, physicists like Rovelli and Kahn suggest the truth might depend entirely on your perspective, that time could be both an illusion and a genuine, meaningful feature of reality, depending on how much of the universe you're able to see at once. Maybe the most honest thing we can say is this: Physics hasn't been wrong about time in the sense of making a careless mistake. It's been wrong the way any science is wrong on its way to something deeper, by mistaking a useful everyday approximation for the final complete truth. And the real story, whatever it turns out to be, is probably stranger and more beautiful than any single theory we have today. So that's the surprisingly unsettled state of one of physics' most basic assumptions, that even after more than a century of relativity and quantum mechanics, scientists still don't fully agree on what time actually is. If you enjoyed this video, please hit like, share it with someone who'd find this fascinating, and if you haven't already, subscribe to the channel. Let us know in the comments, do you think time truly flows, or do you lean toward the idea that it's an illusion built from memory and entropy? I'd genuinely love to hear your take. See you in the next video with a new question and a new mystery to explore. Take care.